Plus meetup, you are invited to. If not, you should boogie on out of here. And you ready, Eduard?
Start?
Yeah, we're ready when you are. All right.
Right, cool. Hello, everyone. My name is Eduard, and I'm a master's student at Polytechnic University of Bucharest. And for the past year and a half, I've been contributing to the D programming language. My main focus was writing a new collections library that takes advantage of the most important features that the D language has to offer. So, first off, safe. Safety is idiomatic to D. And I'm guessing that Walter managed to convince you about the importance of mechanical checks, right? Also, cool. Okay, so we also want to be able to use custom allocators. What? Okay. Let's see if it's an issue with the cable or.
Use the custom allocator.
What the? Come on. So, let's see if extend works. Okay. What the? Okay, so hopefully it helps me. So, as I was saying, safe is at the core of the language. We also want to be able to use custom allocators. And what this means is that now we have to make sure that we are not exposing ourselves to double freeze or use after free, as is the case right here, right? So after we deallocate buff, because we are now doing our own memory management, then buff2 is not who we think he is. Another important part is that we want to provide you with qualified types. Currently, the existing collections in the STD container module aren't qualified. But now we have this option, so yay for functional programmers. And also purity. So purity is important because it allows the compiler to offer us some optimizations, or maybe you care about formally checking your code, right? So now we are very close, actually. We're very close to having this. And why I'm saying it's very close, because we still have to figure out some design details about how the type system can know about no GC. And I'm going to get to that later. First off, let me take you through a journey of the important design decisions that we've took. The most important one was to rethink the way we view a collection. So instead of having the usual approach where you have the store that has like some internal scaffolding for keeping your data and then a range or an iterator that acts as a view over your data, now we're just going to have a range that has some optional primitives that enables to insert to the containers. Everything is self-contained, and why is this important is because it solves, just by design, the dangling range issue, for example. Now you can just return the range and it does its own memory management, it reference counts itself, so you won't be able to like use something that has been destroyed. A second important thing we had in mind was to come as close as possible to a built-in slice that does its own memory management. In other words, when in doubt, do what int slice does. And one thing that we get from being compatible with the Rage API is that we can have seamless integration with the standard library, with algorithms that know how to use ranges. So first, no GC. We said we want to provide custom allocators. An important thing to take note is that the allocator is not part of the container. And this makes very much sense because, after all, a list is still a list. It doesn't matter the allocator that it uses, right? So the allocator is just a means to an end. It's a way we acquire resources from the system in order to represent our data in memory, but it shouldn't define the type. We are going to use one of those two allocator interfaces. So RCI allocator and RCI shared allocator. Those are reference counted structures. They are currently in the experimental allocators module. Sorry about that. And they take care of their own memory. When there's no more reference to one of those objects, it's just going to self-destruct. Another key aspect is that if the user doesn't provide us with a custom allocator that he wants us to use, then we are going to default to a statically known allocator. The statically known allocator is going to respect the following rule. An allocate and deallocate pair is not going to create garbage. And what this means is that we might find a way, a possibility, to actually use even the GC in the backend. This might sound controversial, but just to give you like an incentive, it has to do with disabling the GC and enabling it again. Okay, safety. It should be pretty clear that we want to infer safety from the contained type, right? So just a small parenthesis here. I want you to show interesting idiom that I've found. But Andrei showed it to me, actually. So it's the following thing, right? Let's say we want to create an object of type T. We're using a custom allocator. We can put that entire code in a trusted lambda. And then what we are doing with the if zero over there is that we are going to enable the type system to infer all the attributes that the object, that T, has to offer. So it's going to infer if it's no GC or not, if it's safe for system, right? And it's pretty cool because this is going to be optimized away by the compiler. So we won't have any branch, we won't have any penalty at runtime. So it's pretty cool. I'm using it quite a lot.
Pop quiz question, sorry for the interrupt. Who knew about this trick? All right? Who knows now about this trick? Everybody. So Walter actually discovered it, and I found it really cool. So if zero, it still type checks the code, doesn't run it, doesn't even produce it in the backend, but I think it's an awesome trick. Just if zero and you type check everything.
Why not with false?
A zero is shorter to type.
Lazy. Right. So as I said, we are going to guarantee safety through reference counting. So how are we going to do this? Is we are using one of the custom allocators in the allocators module, specifically the affix allocator. And what the affix allocator does is that it's going to, aside from giving you the buffer that you want to use in order to store your data, it's also going to front a small piece. And another key aspect of this small piece over here is that this is independently typed from the payload. So if, let's say we have a node from our list that's reference counted, and the node is immutable, the reference count for the node is going to be shared. We are using intrusive reference counting, as you can see, so this means that it's actually good for performance because we have less indirections. A thing to take away from this slide also is that, as Timon has pointed out, this might be this is problematic in pure functions when we combine pure and safety. So this is another reason why the keyword __ immutable that Andrei was talking in his keynote earlier this morning is going to help us. So let's talk a bit about qualifiers. I said that now we are going to have support for constant immutable types. So allow me to show you how you would use them. So we're going to provide two primitives. First is tail. For those of you who are accustomed with functional programming, I'm pretty sure that you know what it does, right? So it's going to give us all the other elements except the head of the container. A way we could use it is we have an immutable array over here. We take the tail of it, and then we just access the front element, and it's 2. Another way is each. So the each primitive you can think of as a for each. It's It's taking a unary function, and it applies this function over each element in your collection. A key aspect to it is that if you provide a function that returns a flag each type, then this is capable of early stopping. So as I have the greater than 1 over here, it's going to go through each element of the immutable array and it's going to compare the result. And this is going to stop because exactly the first term is not greater than 1. Okay. So, as I said about Andrei's talk earlier in the morning, right? So Andrei was mentioning about the tail qualifiers. So let's take a look at this code and see what I mean by this. For an int array, fun is going to print at compile time int. For immutable int is going to print immutable int, immutable s, immutable s. But what will it print for this, for an immutable int slice? It's going actually to print a slice of immutable ints. This is the only place in the language that this happens. This is a hack, as Andrei mentioned in the morning, right? But it's proven to be a very successful hack because this allows you to use a lot of algorithms in the existing library with immutable arrays, right? So what we want going forward is that we want to allow user-defined types to take benefit from the same advantages that the array does. And how we are planning to do so, so we're planning to do a design implementation proposal. Let's say we name our function OP template function match. Lengthy name, I know. So every time we are going to pass my range, this object my range, into a template function, this guy is going to get called. And we can use introspection because we have those cool features, right? In order to decide what we want the behavior to be, depending if this is a const my range or if it was an immutable my range. And for mutable types, it's safe to just return this. Just let it through, right? Let it pass. So what this lowers to, as you can see over here, is just a call of X, as I've named it, OP template function match. Okay. I previously mentioned that we are going to use two types of allocators, and now I want to tell you why. So, immutable is implicitly convertible to shared. And what this means for us is that if we were not to use an allocator that knows how to deal with memory allocations in a shared environment, then we would expose ourselves into a race condition. Const is a bit more problematic because we don't know, right, if the const reference came from an immutable object or from a mutable one. So for now, we're just going to take a more conservative approach with const as well, and we are going to require the use of a shared allocator. But for const, this can be relaxed later. So just to recap, we want to find a way of defining a type that knows to store either a thread local or a shared allocator that we are going to use to do reference counting, right? So this is going to be an affix allocator. So the first thought, the first pick was algebraic. For those of you who don't know, algebraic is in the standard library, and what it does, it defines a contained type of valid inputs, of valid types that you can use. Sadly, algebraic is not compatible with shared. We can't use it with shared. But no problem, we're just going to write our own. While we're at it, at writing our own, we also need to take into account that we want to do as int slice does, right? So if you have an immutable type, you want to be able to return a mutable copy from this type. Well, what's the problem with this is because immutable is transitive, and the allocator is stored inside the collection, right? This is going to lock the allocator. The immutable is going to apply to the allocator as well. So we want to find a way of storing a mutable allocator in an immutable collection. Okay, so first things first. We're just going to wrap a shared allocator and a local allocator inside the union, and we want to reference count this as well. Now, taking it further, so the next step, we also want to escape the type system, as we are doing with the reference counting. When we are reference counting an immutable object, we want to apply the same logic to allocators. We want to be able to make this guy a shared type. So that's what the union over there is all about. And I'm going to talk a bit more about its syntax later. So the basic flow of it would be, we have the allocator is going to allocate its own support, and then it's going to move itself in here. And from now on, we're using it from this place in memory. So just a reminder, right, as I previously said, the allocator, named allocator handler, is stored inside the collection. And for when the collection is typed as either mutable, const, or immutable, we're going to have the same, those types, right? So another aspect here is that we wanted to have something that's very specific, this allocator handler, because there are a lot of things going under the hood. We're playing with safety, with purity, with immutability, with a lot of things, so we wanted to have a lot of granularity and control over what we are doing. Okay, so I mentioned purity, so now let's talk a bit about purity. So what is a pure function? From a high-level point of view, maybe we could define it somewhere around here, right? So it's a function that has the same behavior for the same parameters. So it's going to give us the same result for the same input. And it doesn't access global mutable data. So purity is cool because, as I previously said, it helps the compiler optimize our code for us, or we can do static checks. But what about purity and allocators? Where from the type system's point of view, an allocator is impure because it accesses global state. But from a logical point of view, an allocator is just a way of accessing system resources. So, and it's safe to assume, right, that if we have enough memory, then the system is just going to provide us with another fresh copy. And when we have run out of memory, then we already have some big problems there, right? So just throwing an out-of-memory error or returning a null pointer, but it still sticks inside the guidelines of purity. So what this means is that we need to have the allocator functions, allocate, deallocate, expand, all of them, they need to be pure. And in case you did not know, the GC already does this. What's the difference between the GC and all the other allocators in the experimental module? Magic, exactly. So it's magic. The type system knows about the GC and he gets preferential treatment, but it shouldn't. Okay, so the next topic, immutable collections purity are really tricky. Just to recap, we're now going to have an immutable allocator handler. And we want to make sure that the compiler won't optimize away our calls. It's not going to say like, hey, this is immutable. It's not going to change anything, so I can safely just not call this function, right? So it would be problematic for memory allocations. It would be problematic for deallocating. So coming back to this guy over here, I'm just going to go really quick because it's a lot of implementation detail. First off, disclaimer, this is a hack. So the point of this hack is to try and escape the type system, and currently it works. So what we want to do here is, remember that I said we are moving the allocator inside the support? Well, now with this pointer, what we want to do is just like store the address. And the address there is not mutable, it's immutable. But the object at that address we don't know nothing about. So currently this works, but it doesn't necessarily need to work. It doesn't have guarantees. So first thought to take away from here is that we need to improve the specification of pure and what purity does and what the compiler can do with purity. And this comes again as a reinforcement for mutable, which is a way to stop the immutable transitivity. And part of the reason why we came to the conclusion that we need this is because we hit so many problems while trying to implement collections. So currently, we have 4 working examples of collections in the form of a singly linked list, a doubly linked list, an array, and a hash table. And a reference counted string is under development. So what this guy is going to do is going to manage his own memory, and he's not going to do auto-decoding. He's going to decode the string only when we ask him to do this. So I hope you'll, I don't know, find this pleasable, right? Or cool. So the library is available as a .dub package. The code is on GitHub, and you can find the documentation over here. Let's see if this won't break, and I can use an Alt tab. No, I didn't want to play nice. Duplicate. Cool. Yeah, so documentation is stored with the GitHub pages. Thank you very much for your time, and I'm here to answer your questions.
So I have a question. Do you consider appender to be part of the collections, and will that be included as well?
Sorry, could you repeat the start?
It's array appender, so it's not part of the collections set, but do you consider that to be logically part of the collections, and will that be added as well?
So I haven't looked at the appender implementation, so I don't know how this would work with it, but probably if we can find a way of making them work together, then we'll probably provide a separate implementation inside the collections module.
Yeah, so you had the, can't remember the name of it, it was humongous, op change template parameter or something like that.
Okay.
That does work, and it actually has some good uses aside from just figuring out const. But I wonder if you'd considered a function that's not a template that takes a, let's say, a const range, and you want to pass it just a range. If there's any way we can solve that problem as well. Because if you want to basically specify this function won't modify any data in the range.
So maybe Andre might want to take this one.
Embarrassment of riches. So it's a simple lowering. We're simply looking at the lowering here. And you get to define, the example was generic because it was simplest to implement on one slide and very evocative, but it's just, you know, whenever you match the parameter, you go into the lowering, and the user does whatever the heck they want with the lowering, template, non-template, what have you. The details are to be established, but essentially we're going with sure winners, which are lowering to existing decode, the simpler, right? And doing what the compiler already does for built-in arrays, which has been like immensely useful in the sense that everybody was silently happy. It was like a headache that went away. Right?
Yeah, so the compiler already also does a conversion from a const array to a const array slice, even when it's not a template. Is this just the other possibility that does it? Yeah.
If collections are ranges, how do they not get consumed when you pass them to a function that takes a range?
So, well, the post bit is just going to create a copy, like a shallow copy, right? So you're just going to have another reference to, let's say, the start of the list, and you're just like consuming that second copy of it. So
it basically calls .save for you when you pass it in?
Yeah. I mean, the post bit does that for you,
Okay.
or when we'll switch to copy constructor, that is going to do that for you.
Are there other examples of where you need to store a mutable allocator in an immutable array? Because like I found the dupe example fairly bad because like basically maybe the caller of dupe would want to pass its own allocator for the duplicate. Like he wants to make a copy and then he passes the allocator rather than storing it inside the array. So are there other examples where you need it?
So you also need it for the reference count, right? So when the time comes to like free the objects.
So for freeing, yeah.
For freeing as well. I mean, you also need that, right?
Yeah, but that, yeah. Mm-hmm. Yeah, but that's already in memory, the reference count. Yeah, that's the mutable part, yeah.
The D language already supports arrays, just use the square brackets, and it also supports associative arrays. So what are the advantages of the new collections library except the possibility to use custom allocators?
So first off, support for built-in keywords in the language. So now the type system can infer purity and safety and all of those. Another one is qualified types, so constant immutable types, which are you're not able to construct a const array from STD container.
Was the question, what's the advantage over built-in construct slices?
Pardon?
Was that the question, what's the advantage of user-defined collections over built-in slices?
Exactly, yeah.
Yeah, you can add no GC, that's it.
Okay.
Slices work with everything except no GC, and now you can use everything plus no GC. It's like if we get to the point where we have a slice that takes care of its own memory, we're there. That's really it.
Okay, thanks.
Sorry, I misunderstood.
Okay,
the
I
question.
think we're over our allotted time, so I think we're going to have to cut the questions there. If you have more, I'm sure Andre and Edward will both be available after. We want to be back here by 5:40 to start the lightning talk, so it'll give us a little bit of cushion if we go over time. And so thank you very much, Edward.
Thank you.
Lightning talk people, I need you up front, please.